So phasor representation and AC power. The first thing we're going to try to look at is addition of two complex numbers. There are some important things we have to pay attention to first of all, so that you can understand the complex things we're going to do, or the more difficult part of the work we are going to undergo today. So the first thing we will consider is addition of two complex numbers. How do we add two complex numbers together? For example, suppose that we have two phasors that should be added together. What you see here is that we have a phasor one. This is phasor one here. This is a phasor one, and then this is the second one. All right. R1 represents resultant 1, R2 represents resultant 2. Theta 1 represents phase 1, theta 2 represents phase 2. Okay, so this is what we refer to as phasor representation. All right, or you can also call it polar representation. Okay, as you will see as time goes on. So we have this. If you want to add these two together, what you would have is R total and then phasor total. R total represents total resultant. Okay, and then we have theta total represents the total phase or angular phase that we have. So first convert the phasors into rectangular form. Okay, like I told you, this is a polar form. This is a phasor form or polar form. All right, so they mean the same thing. Phasor and then polar, they mean the same thing. Before you can add them together effectively to get this a final answer here, you have to convert these into rectangular form first of all. Converting them to rectangular form would mean that you're converting them into this particular form here. This particular form. This is a rectangular representation. Okay, so this is the polar representation of phasor representation resultant 1, phase 1. It becomes A1 plus JB1. What you will see here is this A1 will represent a constant, and then B1 will represent another constant. All right. This entire JB1 will represent it means it is an imaginary term. This represents an imaginary term where A1 and B1 are constants. The same thing for A2 and B2, they are constant, right? So R2, T2, you write it like this too. Now, if you want to add these two together, it means you're going to have to add and these rectangular forms together or representations together. If you do that, you have A1 plus A2, which will give us A total. So A total will just be A1 plus A2. In this particular case, you can just add them together, all right? And then for B total, how do you handle them? It just becomes J into bracket B1 plus B2 will give us B total. This is important. So how do you find your resultant R from here? How do you find this R total from here? R total will be given as the magnitude of A and B. The magnitude of this vector representation will be A squared plus B squared. You put everything in brackets. That gives you the resultant total. So R total will become A squared plus B squared, all in square root. Okay, so once you obtain the values here, you put it here. And then your phase total phase will be equal to tan inverse of B over A. Tan inverse of the coefficient of the imaginary term here divided by the real term. This is the real term. A is the real term. So it becomes theta equal to tan inverse of B A. Whatever you obtain here, you put it here as your T total. And before you know what is happening, you already have your final response to addition of the two phasors or polar representations that we have. All right. So we've dealt with the addition of two complex numbers. How do we deal with the subtraction of complex numbers? We're going to treat subtraction of complex numbers pretty much the same way we dealt with the addition of complex numbers. That would simply mean that we have phasor 1 here, we have phasor 2. So to subtract, all you need to do is just subtract phasor 2 or phasor representation 2 from 1, all right? Or polar representation 2 from polar representation 1. If you do that, you have this. The only thing that is different here is that, of course, your R1 will still be the same, A1 will still be the same in terms of rectangular representation as before. R2 will also be A2 plus JB2. So in this particular case, what you will find out here is that we are subtracting A2 from A1. In the previous discussion where we were adding two complex numbers, we were actually adding A1 and A2. But in this case, it will just be A1 minus A2 plus J. Don't forget, don't mix it up. This is still going to remain plus. It's not going to change to minus, okay? The only thing that will change to minus, the only place we have minus is going to be between the real numbers and between the coefficient of the imaginary numbers here. So you have A1 minus A2, B1 minus B2 or plus JB1 minus B2. Again, how to find your R from here with the magnitude of A1 and whatever you obtain here as your A total here, A here, and then whatever you obtain here as B here, you use them to find your R total, which is going to give us this. Just find the magnitude, and then the same way you find your phase, and then you get your phase total here. This is exactly how to handle that. Then after dealing with subtraction of complex numbers, the next thing we want to look at is to talk about how to multiply complex numbers. Now, how do we multiply? It simply means that here we have A1 plus JB1, we have A2 plus JB2. All right, when you multiply them together, you have A resultant plus JB resultant. You have A resultant plus JB resultant. That's what you have here. Okay, so now we have the rectangular representation already, as you can see here. Let's assume that we have the rectangular representation already. So to multiply complex numbers, you have to convert them to their polar representation. Okay, you will notice that before we can add complex numbers together, we converted them from their polar representation to rectangular representation. Okay, but now if you want to multiply or divide complex numbers, you convert from rectangular representation to polar representation. If you already have them in polar representation, it's good, you can just go ahead and multiply. All right, but then if you have them in rectangular representation, you have to first of all convert them to polar representation to make it easy, you know, for you to do what needs to be done. All right, so in this particular case, this is in rectangular representation. If it's converted to polar representation, this is what you have. You can see you have R1 and then you have phase 1 here. All right, so you already know how to find R, right? You know how to find your R1. It will just be magnitude of A1 and B1. That's A squared plus B squared. You find the square root to get your R1, and then your phase. After you get the phase, there is going to be tan inverse of this B1 over A1. Then you get your phase 1 here. Okay, that's how to get the polar representation. You do the same thing for the second one. So if you're going to multiply for the second rectangular representation, rather, if you're going to multiply the two together, it becomes R1 multiplied by R2. That's what you have here. It becomes your R1, R2 here. And then this theta 1 multiplied by theta 2, you have to add them together. All right, you add them together. So it becomes theta 1 plus theta 2 to get the total phase or phase total here. So once you have done that and you have it in this particular form, the next thing you want to do is to convert it back to your rectangular form or rectangular representation. Okay, so once you have this, you can go back to your rectangular representation by saying that your A is equal to R cos theta and B is equal to R sine theta. Okay, so this is pretty easy because, you know, if you have a rectangle like this and then you have your theta here, okay, this is usually, let's say this is A and then this is B. All right, and then this is our resultant here. All right, so if you're looking for this A, it becomes easy. You just find your cos theta. What is cos theta from here? Cos theta will be equal to adjacent over hypotenuse. Adjacent here is A. Hypotenuse is our R. All right, so if you're looking for A, your A will just be equal to, you cross multiply, and that gives us R cos theta. That is how they got this A equal to R cos theta here. All right, the same thing for B, you find sine theta. Sine theta is going to be opposite over hypotenuse. That is, sine theta will be equal to B over R, and then your B will be equal to R sine theta. That's how they got these two here. Once you have this, then your, you know, your representation for your multiplication representation for these two rectangular representations given to us will be A resultant plus JB resultant, and then you have solved the problem if you can do this. I want to assume this is pretty much straightforward for everybody. So if you do have questions, please don't hesitate to ask me. I will be more than willing to try to respond. These are simple stuffs, by the way. I expect that probably at some point you would have done some of these things before. If you have done numerical analysis before, or if you've done some further mathematics before, you would have been taught all of these things. So, but in case you've not been taught, I mean, you can still get it from here. And if you've been taught, this is just going to be like a revision for you. What about division of two complex numbers? When you divide two complex numbers, what happens? It means that you're going to follow the same procedure as the multiplication, exactly the same procedure. The only thing that would change is that you will subtracting the phase angles, and then you will be dividing the resultants, okay, into the polar resultants here. Instead of having R1 multiplied by R2, you have R1 divided by R2 here. All right, so this is exactly what is different. Right up till this level, up to this point, the process is the same with the process is the same with the multiplication of two complex numbers. But here, instead of multiplying, you divide R1 by R2, and then instead of adding theta 1 and theta 2, for division, you subtract theta 2 from theta 1, and then you find your A the same way we found it when we were multiplying. You find your B the same way, and then eventually you have your resultant. Don't forget, for the resultant, this is also not going to change to negative. This remains positive. So let's take it a step further and let's see other important things to discuss. All right, so properties of J operator. Okay, this is important. The J operator is a complex term, is what we use to define an imaginary term in complex representations. Multiplication of a complex number by J operator shifts or rotates the angle of vector by 90 degrees, while the magnitude is unchanged. Okay, the magnitude remains unchanged. So J by definition is given as 1 with phase 90 degrees. Okay, J equal to 1 phase 90 degrees. So if you multiply a complex number 4 with phase 60 degrees by J, it simply means that what we are going to have is the magnitude is going to remain the same, just like we said that the magnitude remains unchanged, but then we are going to rotate, the direction is going to change. So this becomes 4 phase 60 as we have here multiplied by J. Okay, and since our J is 1 phase 90, this becomes 4 phase 60 multiplied by 1 phase 90. All right, 4 times 1 becomes 4, because like we said, this is not going to change, it remains 4. So you have 4 here, but then there will be a shift, there will be a rotation, the angle would have changed. That means the direction would have changed to a large extent. So what you have here is you have 60 degrees. Since we are multiplying, it becomes 60 plus 90, and that becomes 150 degrees. So multiplying any complex number by the J operator has shifted this by 90 degrees from 60 to 150 degrees here, the magnitude remaining constant. Okay, so this is the initial, this is J operator here, as you can see here. This is J operator, J here on the vertical axis here. Okay, the J operator on the vertical axis, and as you can see, like we said, the magnitude is 1, and then the phase is 90 from this is 0 degrees, you know that already. So if you move from 0 degrees to this point, that is 90 degrees. Okay, so this is our J operator. So if you multiply this J operator by 4 phase 60, 4 phase 60 by 4 phase 60, it means we have this phase here. This is 60 degrees. Okay, moving from here to here. So that means we are multiplying this phase 60 with magnitude of 4 by this 90. And then the resultant will give us 150, as you can see here. So you can see what it looks like. This particular representation here, this graph here, shows us the representation of both J alone, all right, then the complex number given to us, and then the resultant when both of them are multiplied together. This is exactly what we obtain. So you should be able to interpret this. All right. So the powers of J. Okay, so the most important thing for you to know here is that J squared is equal to minus 1, all right? So if J squared is equal to minus 1, what is J cube? J cube would just be equal to, J cube will be equal to just J squared multiplied by J. That's what it simply means. J squared multiplied by J. Since we know J squared to be minus 1, this becomes minus 1 multiplied by J, and that gives us minus J. Okay, so that's why you have minus J here. What is J raised to power 4? J raised to power 4 will just be equal to J squared multiplied by J squared, and that will be minus 1 times minus 1. That gives us plus 1. What is 1 over J? 1 over J is always equal to minus J. Okay, this is important. 1 over J is always equal to minus J. Pay attention to that, because we would also use this a lot. Okay, so these are the various representations of all of these in graphical form. You can check them out and see how J is shifting them, because we say multiplication with J, shifts, the phase of any complex number. Okay, it shifts or rotates that complex number. Okay, so multiplying by J, this is exactly what happens, and then you can check them out, see what is going on, and then, for example, when you multiply, when you have 1 over J here, all right, so for j cubed is equal to minus j, you can see that this is more like a total reflection. Instead of going this way to get your j, you just come this way, it becomes minus j. Okay, that's what we have here. So this is important for all of us. All right, let's take it a step further. You can see this is j squared, this is j cube, which is the same thing as 1 over j, by the way, and that is minus j, and then this is j raised to power 4. Now let's look at phasors. Now that we have the understanding that we have, let's look at phasors. The first thing you should pay attention to, we've talked about the Euler identity before. So the Euler identity is usually given as exponential j theta equal to cos theta plus j sine theta. This is very important. Exponential j theta equal to cos theta plus j sine theta. All right. And the magnitude of that will give us magnitude of cos theta plus j sine theta divided by the square root of cos theta squared plus sine theta squared, and eventually this gives us 1. So the magnitude of E j theta, the Euler identity, is always equal to 1. All right, so this is important for us. If you draw that on a rectangular graph, what you have, or if you draw it on your coordinate axis, this is going to be our resultant magnitude, which we obtain as 1 here. This is 1 here. And you know what sine theta is? Sine theta is going to be opposite over hypotenuse. So whatever you have here divided by 1, and then cos theta will be equal to, by the way, this is going to be A, okay, this is going to be B, all right? So you can easily treat all of these just the way it is here, all right? I've given you this representation before. You have your resultant, you have A, you have B, so you can easily find your A, your r squared, the resultant, using the Pythagoras theorem, all right? So you have r squared equal to a squared plus b squared, r equal to the square root here, all right? And then you can easily find your theta too, which will be tan inverse of b over a, okay? So these are pretty simple stuff. These are still mathematics, okay? We'll start dealing with the electrical, the engineering part of it in a bit, okay? But you need to know this, because without this mathematical understanding, you may run into some problems when we start dealing with the other big stuffs. Okay, let's go ahead. So what are sinusoids? Sinusoids usually have they are graphs, or they are signals that have the sine wave graph. All right, sinusoids are signals that have the sine wave graph. Okay, you know what a sine wave graph is? When you have something like this, and you have these here, and then you have these, and then you go this way. All right, so sinusoids have sine wave graph, okay? As you can see here, this is a sine here, so that's where they got the name for sinus. Sinusoidal sources are of great interest, especially when we're dealing with AC signals. Power grids carry sinusoidal AC signals. Any signal can be represented by summation of sinusoidal signals of different frequencies, okay? So that simply means that we could have a frequency, a fixed frequency, okay, for a signal, then have another frequency again for a second signal, or another frequency for a third signal. You can combine all of these different, signals together that have different frequencies, okay? So what you find here, you have V of t. You all know what V of t is. V of t is equal to Vm sine Wt plus phi. All right, our phi here represents our phase angle, all right, okay? And then you can see we have sine here, and you can see it's going to represent a shift in our phase angle, by the way. W here represents our angular frequency, and this is our phase angle. And then you can see we have sine. Vm here will represent our amplitude. If this is V of t, and this is going to be V of m, so this would be our voltage amplitude, because this is V of t. This is V at any instant of time t. This is going to be the amplitude, or the peak value of the voltage, or the maximum value of the voltage. W is equal to 2 pi f, we know that. Okay, so from here we can say that f will be equal to 1 over 2 pi. We can say that, okay. We know that our f also is equal to the inverse of the period. We have been taught this, okay, so let's just remind ourselves. F is equal to inverse of period. From here, f equal to 1 over 2 pi. So we can easily say that 1 over period t is going to be the same thing as 1 over 2 pi. We can easily say this, which is exactly, what we'll have here. This is going to be f equal to w, rather, not 1. This is going to be w over 2 pi here. All right. So please keep this in mind. We're going to use it too as we go on. And then keep this equation. Please keep that equation too in mind. V equal to the amplitude of V sine into bracket WT plus the phase angle, or the angular frequency plus the phase angle, where the units are radians per second for W, and then for the frequency, the unit is hertz, as you already know. Okay, so for our phasors, you will find out that we can have two kinds of sources here. We could have a cos WT plus phi, we could have a sine WT plus phi. Okay, so this source can be represented in the complex term in the following way. You have the source, the complex source representation becomes A exponential J WT plus phi. What you will find out here is just this WT plus phi is the same thing that we have here. We added J here, and then everything, we have exponential here, and then this A remains here. This can also be represented as a phasor. All right, this source can also be represented as phasor. Since we are dealing with AC signals, okay, so it could be cos to come in terms of cos or in terms of sine. If it were to be a DC signal, the source will be constant, like 12, like 20, like 30, like 50, like we have already done in the previous classes, okay, previous discussions, okay. So if it were to be DC sources, this is going to be constant. But if it is AC source or AC signal, they always come in trigonometric expressions like this. It could be cos or it could be sine. So whatever it is, whether cos or sine, this is how to represent them in either complex representation, either using complex representations or phasor representation. This is exactly how to represent them. So for a cos WT plus phi, this is what you have for phasor representation. This A is the same A that you see here, and then this phase here would be the same phase, that you have here. All right, so that's that. Then for A sine WT plus phi, what you have here, it's pretty much the same thing. The only thing, instead of having just the phase here, you have phase minus 90 here. That's what you have. Instead of having just the file here as the phase, it becomes phase file minus 90 as a phase here. So what you have here is going to be the A, which is still the same A here, which is still the same A here, which is still the same A here, and here you have A. Then the phase would have changed to theta minus 90. So whatever you have here after this WT plus, whatever you have there becomes what you have as your phase angle. All right. So this particular representation here. What it tells us is that this is our magnitude or resultant or amplitude, and then this is our phase angle. This is what it tells us. This is what this represents in phasor form or phasor representations. Okay. The phasor representation reduces the complexity of analyzing second and higher order circuit as long as frequency remains constant. Is a way to represent or reduce complexities of analyzing second and higher order circuits. This is very important for us, okay? And when we say phasor, we're talking about representation in the frequency domain, okay? When we say phasor, it's representation in frequency domain, okay? So that is why we're talking about our angular frequency W all the time. Okay, so this is a rectangular form here of a signal. This is a rectangular form here. Okay, so you can see we have gamma plus JW, and then this is a polar form or a phasor form. All right. How do you find your A? A will be equal to gamma squared plus W squared. Put everything in bracket. That's how you get your A. This is important for you. How do you get your phi? It becomes tan inverse of W divided by gamma is what gives you your phi. All right, let's take it a step further. You do know, as we have discussed in previous classes, our V equal to Ri. This is Ohm's law, if you remember. V equal to Ri. So if we also said in the previous discussion that the same V is equal to Vm phase, Vm with phase V, okay, where this represents the peak or amplitude and this represents the phase angle, this is the same V. Our I will be Im with phase I, as you can see here. Okay, so this is also very important because in many cases we have to work with these representations. Phase V and phase I will certainly be the same because there won't be any phase shift there. So phase V and phase I will be the same. Only this Vm and Im will change for different parameters. In this case, current and voltage. Okay, so taking it a step further, what we do have is For an inductor, this is for the resistor, by the way. So for an inductor, things are going to be a little bit different, and I'm glad we've talked about inductors at length before, so this is going to be very easy for you to comprehend. Our V is always equal to JWLI for an inductor. Don't forget, for an inductor, V equal to, we had said earlier on when we were talking about an inductor that V is always equal to L di dt. You remember this, right, with respect to time. So that L is what we have here. This di dt is the current we have here. All right, so this JW here tells us that this is an imaginary term and this is our angular frequency because we are in the frequency domain. Okay, so we have all these, and then we can go ahead and say that V equal to JWLI, which will be equal to JWL. Now, this I would be equal to IM. Can you see that? IM with the phase angle I. Okay, so you can write this way since we already said this is our I here. You just put that in here, it becomes JLIM phase I. And we do know that J is equal to 1 with the phase of 90 degrees. We know this, we mentioned this a couple of minutes ago. I mean, a few discussions ago, we mentioned this. So if this is J and then you decide to replace this J with this, what you're going to have is this V will be equal to 1 with phase of 90 degrees multiplied by L, W, L, and IM. What you find out here is that we are multiplying these. We have phase of I multiplied by phase of 90. When you are multiplying these two phases, the way to treat them is to just add them together like we discussed. Okay, so it becomes file I plus 90 degrees, as you can see here. So this becomes a phase. There's been a shift, as you can see here, because anytime you multiply any complex term with a J operator, there's going to be a rotation, there's going to be a shift. So you can see that there is a shift by 90 degrees. So you have file I plus 90 degrees, and then you have your W is still here, your L is still here, and then we have replaced our I with IM, okay, and the phase here. And then the J is not here anymore because we replaced the J with one phase 90 degrees. That's why we have these here in the first place. Okay, so this is what happens when we're dealing with inductor. And don't forget, in an inductor, we said that current lags the voltage by 90 degrees. Okay, this is what happens in an inductor. Okay, what happens in a capacitor? How is this represented when we're talking about capacitors? Okay, for capacitors, it's voltage equal to I over JW. See? And we know what our I is. Our I is IM, okay, with this. This is our IM, all right, we know that. So this will imply that I, if you cross multiply, instead of for capacitor, instead of substituting IM for I, we can make I the subject of the formula and then we substitute it into V. All right. We make I subject of the formula. You have I equal to JWC now, as you can see here. Okay, multiplied by V. But our V is the same thing as VM with the phase angle of V. Okay, so you have VM here, instead of writing just V, you have VM phase angle of this V here. By the way, this J also can be one with a phase angle of 90 degrees. So if you multiply that, what you have less is just going to be I equal to W CVM with a phase angle of 90 degrees. There's going to be another phase shift here of plus 90 degrees. Okay, so this is very important, and then we can take it a step further here. For inductor, you can see we have V equal to this. For capacitor, you can see we have I. You can see that we have our I equal to this. And in the capacitor, the current always leads the voltage by 90 degrees. In the capacitor, the current always leads the voltage by 90 degrees. Okay, so this analysis is important for you and for every one of us if we would understand the upcoming discussions properly. Okay, let's take it a step further. So now let's talk about impedance and phasor circuits. The ratio of phasor voltage to phasor current is called the impedance. So phasor voltage to phasor current, note that down, is going to be given as our impedance. The impedance is represented as Z, and the unit is usually ohms. All right, as you can see here. And I remember when we started, this class, I talked about admittance and impedance. And I told you that admittance is just the impedance, the inverse of impedance. And the unit of admittance is going to be mho, okay, not ohms, okay? And it is usually given as the inverse usually given as the inverse of ohms. This is the unit of admittance. Okay, so you probably just want to pay attention to this. For any component, our V would then be equal to Zi, because this our Z, like I told you, is measured in ohms. And once you find our impedance, you just use the Ohm's law and say V equal to impedance multiplied by I. This time around, not just multiplied by R. R is just going to be the resistive side of the circuit or of the analysis. For this case, we're dealing with both R, we're dealing with inductors, we're dealing with capacitors, and so on and so forth. So in this particular case, our Z will be the combination of everything. Okay, so this is going to be impedance. So Z impedance will be called the magnitude of Z with the phase angle with respect to the Z. Okay, you can see that. So, and this magnitude of Z impedance will be equal to Vm over Im. Can you see that? It's going to be Vm over Im. And then multiplied by, and then you can see, because this is Vm, this is Im, our Vm here would have a phase angle of this. Our Im will have a phase angle of this. So since we are dividing, that means we are subtracting phase angle of current from phase angle of voltage. That's why we have these here, like I explained to you when we are dividing complex terms. And then our Vm over Im remains constant. Okay, so your V is equal to Vm magnitude. You have this here. Okay, and then you have the phase of V here. All right, and then your I, like we just discussed, will be equal to Im. And then you have the phase angle of I like this. So you have, if you put them over like this way, if this goes up, it becomes phase V minus phase I at the end of the day when you are divided, and then you have your Vm over Im, which is exactly what they did here. So in the rectangular form, how do we write the impedance in the rectangular form? Impedance Z will be equal to R plus Jx, where R represents the resistive component, and then X here will represent the reactive component. So this could be X, could either be XL, or it could be, X could also be XC. Okay, it could be XL or XC. Okay, in any case, they call it reactive component, while R represents the resistive component. Okay, so you can see here your ZR will be equal to R. That's what we can see here. ZR will be equal to R. So impedance with respect to resistance will be equal to R. ZL will be the impedance with respect to inductance. So that will be equal to JWL. All right. So our XL will be equal to WL. Please take note of all of these things. And then our XC will be equal to minus 1 over WC. As we know, ZC will be equal to 1 over JWC. All right, 1 over J will be equal to the same thing as minus J. So you have minus J over WC here. So that's why you have 1 over WC here, because J itself is usually given as 1 with phase angle of 90. So if you bring that here, all right, you're going to have all of these. Okay, and because we have minus here, as you can see, because we have minus here, it becomes minus 90 here because of this minus. So that minus is not going to reflect in this expression here anymore. It reflects in this particular reflection or rotation, you know. Okay, so if we take it a step further, what do we have? We know what our XL is, the reactive component of the inductance, we know it XL. The reactive component of the capacitance, we know it is going to be XC. The reactive component of the resistance is just going to be ZR, which is going to be equal to R. Okay, so let's take it a step further. So for phasor circuit, sources and components are replaced by phasors and impedances. So it simply means KVL, KCL, parallel and series component rules will apply as if all impedances are resistors. So we'll keep using, you know, all the knowledge we've been accumulating, that we've been discussing for a while, will be implemented and used here. So now waveform representation of resistive circuits. All right, so right now we're going to talk about waveform representation of resistive circuits. If you look at the right-hand side here, you will find that we have a simple circuit, a simple resistive circuit here. This is the voltage source of our AC signal, and then this is the resistance that we have in connected to the circuit. And what you can see here is going to be the current from the source voltage from our source. This is going to be a source current. So we do know that our voltage source Vs is called V cos Wt, where W represents the angular frequency, and then the V with the heart on top of it represents the amplitude. That's the peak voltage or the maximum voltage. Okay, and then Vs represent the source voltage. IS, according to Ohm's law, which is the source current, will therefore be equal to the source voltage divided by the resistance, in the circuit. Okay, since we already know what the source voltage is, which is V cos WT, we just replace the source voltage with that, and then that gives us this expression here, Vs cos WT divided by R. Vs over R would be equal to I, which is going to be I according to Ohm's law, by the way. So eventually your Is of T will be equal to the I, will be equal to that I cos WT. Okay, and this I would mean the maximum current or the peak current or the amplitude of the current that we do have in the circuit. Okay, so what you can see here is what the graph looks like. You can see the orange color represents the voltage graph, the blue color represents the current graph, while you can see on the horizontal axis here we have with the angle in radians on the horizontal axis. Now, what you will see here is that for the waveform representation, we are saying that there is no phase shift. There is no phase shift because all we are dealing with is just resistive circuit. Okay, so we have V source voltage Vs equal to V cos WT plus 0 because there is no phase shift at all. What you will find out here is that on the horizontal axis, both of them are crossing the horizontal axis at the same time. So the current and the voltage, there is no leading or lagging between the current and the voltage, so there is no phase shift at all. All right. So what you see here is because there is no phase shift, you add 0 here. Okay. So it's just as good as writing just WT without anything. All right. So our Is of T also will be called cos of WT plus 0 multiplied by I. Okay. The phasor representation would be VSV. With the phase angle 0, and then the source current will be equal to the I magnitude, which is the magnitude of the current with a phase angle of 0. Okay, so you can see the waveform representation and how it is translated to the phasor representation, and then putting all of this together, we can find our impedance. Like we said, our impedance would be equal to the phase voltage divided by the phase current. Okay, so if you do that, you can see we have the impedance to be equal to the phase voltage over phase current, and that gives us the impedance. So our ZR, this is going to be ZR, by the way. So our ZR would be equal to R at the end of the day. You can find magnitude of Z, which is going to just be equal to R squared, and that would be equal to R. Okay, so this is exactly what we have here. These are the important things I want you to pay attention to, how you can move from waveform representation to phasor representation, and then how you can find your impedance and then the magnitude of the impedance, and of course the angle of the impedance. This is very important for you, so please pay attention to that. Let's quickly go ahead. Now we will talk about the waveform representation for inductive circuits. Okay, waveform representation for inductive circuits. So let's quickly look at what that looks like. On the right hand side here, what you will see is a simple inductive circuit. All right, you can see we have replaced the resistor with an inductor. Our voltage remains V of T equal to V cos WT. Now I current is going to be I sin WT. This is very important by definition. I sin of T equal to I of T, or I source current equal to I sin T, where I still remains with a heart on top of it, still I with a heart on top of it still remains the amplitude of the current. Okay, so Vs of T, according to inductive analysis or inductive circuits, we had said long before time that our V is always equal to L di dt. We know these already. V equal to L di dt, and that is exactly what we do have here. Okay, so what you will find out is that this will be equal to L Wi cos Wt. This will be called L Wi cos Wt, because we said this is our I. All right, so to find this I, we just differentiate this our I equal to I sin WT. So when you differentiate I, sin WT, what you're going to have is di dt. When you do that, exactly this is what you're going to have. You're going to find LW here. For example, this is WT. If you differentiate it, you're going to have W. That W goes to the back. Okay, so you have W here, multiply with this L, you have LW. And then you have this I still here, you keep it that way, and then sin WT, when you differentiate that, it gives you cos WT, and then you have it this way. Eventually, what you will find is that this LWI on its own is equal to what we refer to as the voltage, if you remember what we discussed in our previous teachings on inductive circuit. So this is going to be our voltage on its own. So bringing that in, and that is the amplitude of the amplitude voltage, by the way, the maximum voltage. So bringing that in here, you have V cos WT. So, okay, you know this already, V equal to LWI, and then we have that. So what is important is that at the end of the day, IS of T will be equal to I sin WT, which will then be the same thing as I cos WT minus 90. This is very critical. This is very, very important for us. All right. Cos WT minus 90 is the same thing as sin WT. Cos WT minus 90 is the same thing as sin WT. Okay, so you can represent these two as the same. Again, how you demystify what we just explained right now for inductive circuit, Vs is going to be equal to V cos WT. Is going to be the waveform representation for our voltage in an inductive circuit. Is is going to be equal to I cos WT minus 90 is going to be our waveform representation for the current in an inductive circuit. And then you can move from the waveform representation straight up to the phasor representation. So for the voltage, it becomes voltage, source voltage equal to V with an angle, phase angle of 0, all right? Because you can see here, this is just WT, it's not WT plus or minus anything. But for the current, you see we have WT minus 90 degrees. So there's a phase shift. So you can see there's a phase angle of minus 30 degrees. So it becomes, source current will be equal to I, which is the amplitude of the current, and multiplied by the phase angle and the phase angle of the current that we do have here. That gives us minus 90. So what you can see here is that you can see there is a phase angle, right? So V represents our voltage. The orange color here represents our voltage, and then the blue color represents our current. And then as you can see on the x-axis, you can see that current is actually at this point here, and then the voltage is at this point here, all right? And then this angle in degrees can be 90 degrees. This is very important because, you know, we always talk about the fact that there is a leading and there is a lagging between the current and the voltage at every point in time, depending on whether it is an inductive circuit or a capacitive circuit. All right. So if we take it a step further, what you find out is that we have these here, and then you can go ahead and find your impedance. How do we find our impedance? It's just going to be the phasor representation of the voltage, phase voltage divided by the phase current. All right. So that gives us V over I. Okay, V phase angle 0 over I phase angle minus 30, and that gives us LW 90 degrees at the end of the day. Okay, so and our Z is equal to JWL. Our Z will be equal to JWL. All right. Why is it JWL? Don't forget, we had said right from the beginning that our J is always equal to 1 by definition with a phase angle of 90 degrees. This is our J. Okay, so here you just put LW here, and then this whole stuff will be equal to J, and then that's how J appeared in this particular expression. If you want to find the magnitude Z of the impedance, all right, it's going to be R squared, where R is going to be resistive part of the circuit, plus WL, the inductive part of the circuit. Okay, that's how you're going to do it to find your magnitude of Z. All right, and then if you want to find the phase angle, it will be tan inverse of WL over 0, and that gives you 90 degrees. That will be tan inverse of infinity, by the way, and that gives you 90 degrees. And then this expression is important. V equal to LWI. This is very important, especially we mentioned it in the previous slides and discussions. Okay, so this is important. Pay attention to it. So after here, the next thing we want to do is to talk about waveform representation in capacitive circuit. How do we deal with waveform representation in capacitive circuits? All right. So you will find out here that our Vs, our source voltage, again is equal to V cos WT, considering the right-hand side simple circuit here. And then what you will find out here is that our I, source current, will be equal to C d dV dt. All right, C dV dt is what we do have here. Our source current is going to be C dV dt. Okay, so, and that's exactly what is written right here. If you go ahead and say, okay, this is our V, and we're looking for dV dt, what we need to do is just differentiate this to obtain our dV dt. So if you differentiate this source voltage with respect to t, this is what you're going to obtain. You're going to obtain C, which we already have here. This W, if you differentiate this, is going to come to the back. You have CW, and then again we already have this V somewhere at the back here. So CWV here represents our maximum I, the peak I. All right, and then we have cost WT. If you differentiate cost T or cost WT, it gives us just sin WT here. All right, so eventually you find out that your I source current with respect to time at any instance of time in the capacitive AC circuit, what you find here is that it is equal to I cos WT plus 90 degrees, because WT plus 90 degrees will be the same thing as minus sine WT. By the way, when you differentiate cos, you get minus sine. So this minus is going to appear here. The minus is going to this minus is going to appear here. So that's why you know that cos WT plus 90 is the same thing as minus sine WT. So that's exactly what we have here. You should pay attention to these. Also pay attention to this expression. Okay, these are the most important things that we'll be making use of in our calculations, in addition to other things I'm going to point out to us very soon. All right, so let's take it a step further, and then we'll see what's going on. At the end of the day, if you want to represent, the waveform representation of the capacitive circuit for voltage source will be given as V cos WT. This is going to be the phasor representation. You can see we just have Vs equal to V with a phase angle of 0. But this time around, the phase angle is going to be 90 degrees, not minus 90, because we know I of t will be equal to I cos WT plus 90. Don't forget W is our angular frequency. So to find the impedance, to just be Vs over Is, and that gives us the following: V phase angle 0 divided by I phase angle 90, and then V over I is going to be Z, as you can see here, and then this becomes 0 minus 90, because when you are dividing for the angles, you subtract the angle at the denominator from the angle at the numerator, so you have 0 minus 90, and that gives us minus 90 degrees here. At the end of the day, this is going to be equal to 1 over CW, because we know our Z is 1 over CW, by the way. So this becomes 1 over CW phase angle of minus 90 degrees. Don't forget, we had said earlier on that 1 over J is the same thing as equal to minus J. Don't forget, we've talked about that before now. 1 over J is the same thing as minus J. So our Z here will be equal to 1 over JWC, all right, which will be equal to phase angle of minus 90 degrees divided by CW. Eventually, you come up with minus J over CW. If you want to find the magnitude of that, it's going to be R squared plus 1 over CW squared, which is 1 over CW as it comes up here. And then if you want to find the angle, it becomes minus CW over 0. Tan is here becomes infinity, and tan inverse of infinity gives us minus 90 degrees. Okay, so you should pay attention to these, and then some of these important points that we're raising here. So we have a simple example here. Use phasors to find the AC steady state current if V of t, as you can see here, we have V of t is equal to 12 cos 1000 t plus 30 degrees. All right, so what you can see here is that this W is equal to 1000. That's what you can see here. So pay attention. That's the first thing you want to pay attention to. W will be equal to 1000 here plus 30. This is going to be our file. That our file will be equal to 30, as you can see here. So if voltage is equal to 12 cos 1000 t plus 30, and the component below is either R equal to 4 kilo ohms for the A part of the question, or the component is an inductor of L equal to 15 milliamp, or a capacitor of 1 over 2 microfarad. Okay, so in this kind of a situation, how do we solve the problem? How do we deal with it? I'm going to show you right now in a very simple and straightforward manner. All right, here is it. First thing you want to do is to prepare the phasor representation of what we do have. How do you prepare the phasor representation of what we have here? We've been told that we have, this is V of t, okay? So the phasor representation would be normally V of t is usually just supposed to be the maximum voltage or the peak voltage with an angle of the voltage. This is what we usually have. If you remember, we talked about this just a few discussions ago. We talked about this. Okay, so in this particular case, our V hat is 12. V at is 12 in this case, and our phase angle, voltage phase angle is 30 degrees. So to write this in the phasor form, it's going to be 12 with an angle, phase angle of 30 degrees. That is what you're going to have there. Please pay attention to that. That's how to get that. Then again, if we go forward, you want to now try solving the problem. We're asked to find the AC steady state current. Don't forget, the steady state current, I will be equal to the impedance divided by, we're going to actually have to find the impedance divided by the voltage over impedance according to Ohm's law, because normally V is supposed to be IR, so V is going to be I times Z, so I will be equal to V over Z. So the phase angle, the phase voltage divided by the impedance would actually give us the current that we're looking for. In this particular case, we already know that our Z is equal to 4 kilo ohms, which is the same thing as 4,000. So if you want to write this Z in phase, in a polar form or a phasor form, it becomes 4,000 with a phase angle of 0. Don't forget, we are dealing with resistance here, so the phase angle is going to be 0. Okay, so we have 4,000 with phase angle of 0, and then our I will be equal to voltage V divided by the impedance. Okay, so the voltage V here is the phase voltage, is the voltage in phasor representation. So that is 12 with an phase angle of 30 divided by 4,000 with a phase angle of 0. If you do this, this gives you 3 milli. That's 3 times 10 raised to the power minus 3. Okay, that's 0.003. So that's why you have 3 times 10 raised to the power minus 3 here. The angle is going to remain the same because it's just going to be 30 minus 0. Okay, 30 minus the phase angle at the numerator minus phase angle at the denominator, and that gives us 30, and that becomes 0. So this becomes the current that we're looking for in phasor form. Okay, so you want to write this current in waveform representation, with a waveform representation. If you want to do that, it becomes easy. All right, what you have here, this 3 here represents this is milli, by the way. So if you want, you can just write these as 3, and then the angle is 30, and instead of writing amperes, you put milliamperes here. Okay, so that milli, this 10 to the minus 3 can become milli here. If it becomes that, this 3 becomes the amplitude of the current, the peak current, maximum current. So that becomes 3 cos, because that's what you have here. That's what you should have here. That becomes 3 cos WT. Here is our W from the question. We know that. So you still have WT plus 30 degrees milliampere. And this becomes the final current that we're looking for in the real sense of it. We should go ahead and talk about the current for when the component is an inductor of 15 millihenry. You do know that our Z for an inductor, our Z will be equal to JWL. We know that already. And since you know our J is equal to 1 with a phase angle of 90 degrees, phase shift, a phase angle of 90 degrees. So we can remove this J here and replace it with this. And this is what we would obtain if we do that. So you have WL with times 1 with this angle of 90 degrees. At the end of the day, our W, from what you can see here, our W is 1,000. I told you earlier, W is 1,000. Our L is 15 millihenry. So if you multiply that, the 1,000 and the milli will cancel out, and what you have left here will just be 15. So you have 15 with a phase angle of 90 degrees. Again, what we are looking for is our current. So we can say our current will be equal to the voltage in the waveform in the phasor representation or polar representation divided by our impedance in that same representation, polar representation. So you have current will be equal to V divided by Z, and that gives us 12 phase angle of 30 divided by 15 phase angle of 90. 15 over 12 over 15 should give us 0.8, which is the same thing as 3, that is 4 over 5, that's 0.8 with an angle of 30 minus 90. Okay, this is in the bracket, because I would treat the phase angle is the phase angle at the numerator minus phase angle at the denominator gives us the total phase angle. So it becomes 30, especially when we are dividing. So this becomes 30 minus 90, and that becomes 0.8 with a phase angle of minus 30 degrees. Again, we can write these in a waveform representation, which is what is expected of us. in many cases. So what you do is I becomes this becomes a peak. This 0.8 becomes a peak. It becomes here 0.8. Course WT. You already know what W is 1000, so it becomes WT. You just pick these up here. You notice that there is no plus. It is now a minus. In the first one, there was a plus here. Why? Because this 30 has plus. This 30 here is plus. 30 degrees, the phase angle. Here, the phase angle is minus. So it becomes minus times plus here, and that gives us minus 60 degrees ampere. This is how to treat the case if L equal to 15. Then again, what happens? Again, what happens if C is 1/2 microfarad? Now, this becomes very easy for you to be able to handle. Since we have done A and B, you should be able to handle this on your own. So I'm just going to quickly try to go through it briefly for us, and then we can move on from here. Okay, so in that particular case for capacitors, our Z equals minus J over WC. We've talked about this before. Minus J over WC. Don't forget our minus J will be equal to 1 with a negative angle, minus 90, here, because our J cube, we mentioned this, J cube is supposed to be equal to J cube is going to be equal to minus J. J cube is the same thing as minus J, because J squared equal to 1. We mentioned this when we started. J squared is 1, all right? So, and then J squared is supposed to be minus 1. And then J cube will be J squared times J. So our J cube will just be minus 1 times J, and then that's how we got this minus J. So J cube is the same thing as minus J. All right, so if you have minus J here, the expression for J cube is 1 with a phase angle of minus 90 degrees. So since they are the same, you just bring that here. Again, our W is 1000. Our C is 1/2 microfarad. 1/2 microfarad is the same thing as 1/2 times 10 raised to power minus 6. 1/2 is 0.5. So 0.5 times 10 raised to power minus 6 times 1000 eventually, with one divided by all of those would eventually give us 2000. Okay, so you can practice that at home to be sure what is going on here. So it becomes 2000 with the phase angle of minus 90 degrees. Again, our I will be equal to V over Z, as we discussed. So we know our V to be 12 with the phase angle of 30 degrees divided by our impedance, which is now 2000 with a phase angle of minus 90 degrees in the case of the capacitance, capacitive circuit. So this then, if you divide this, it becomes 6 times 10 raised to power minus 3 with a phase angle of 30 minus, the phase angle is going to be 30 minus 90, because when you divide, you subtract the phase angle at the denominator from the phase angle at the numerator. So it becomes 30 minus 90, and that becomes 30 plus 90, and that gives us phase angle of 120 degrees. So you have 6 times 10 raised to power minus 3 with a phase angle of 120 degrees. Again, this is milli, so you can bring this here, it becomes milliampere, and then all you have left is just going to be 6 here. So you can put 6 here as the peak voltage, and peak current rather. You can put 6 here as the peak current, cos WT plus the phase angle, all right? The phase angle is 120 degrees, so it becomes plus 120 degrees. Don't forget, this milliamperes is what is eventually represented here at the end of the day. All right. So we have a second example here, and in that second example, what we're talking about is a circuit that has both a capacitor and an inductor and a resistor. Okay, and then we have our voltage source here. So the question says, find first mesh current. Find the first mesh current. Before now, we've talked about first solution before. Okay, we've talked about first solution before, so we're going to apply that knowledge here. So find first mesh current, I of t, first of all, without using phasors, and then using phasors. Okay, we have the circuit, so you can see we have the capacitance 1/10 farad, the inductance 2 Henry, and then the resistance is 2 ohms. This is our source voltage, is an AC signal. From here, you can see that our W already is going to be equal to 2. W would be equal to 2 here, because normally it's supposed to be 15 cos 2t plus the phase angle, and the phase angle we have here for the voltage automatically is 0. As you can see here, we can see we have 2t plus, there's nothing right in front of it, so it's just like saying we have 2t plus 0. So from here, we have these two analyses here. So if you take it further, what do you see? You want to apply KVL here. If you apply KVL, you have, let me clean this up a bit to make it easy. So if you apply KVL here, what you have is L di dt starting from the inductor. You have L di dt, okay? So our L is 2, so you just put 2 di dt plus 2I. This current is passing through 2 ohms, so V equal to IR. 2 times I will be voltage across the 2 ohms resistor here. So you have plus 2I, then plus 1 over C integral of I of t dt. Okay, so we've talked about this definition before too, from the initial, charge to final charge, to charge at any time t. So you have from 0 to t. So you have 1 over 10. Okay, 1 over 10 is the C. So 1 over C is what should be here. 1 over 10 will give us 10. That's why we have 10 here instead of 1 over 10. So you have I of t dt plus Vc of 0. This will represent the initial charge. Okay, the initial charge before, start charging the circuit. All right. So eventually, if we continue, this is supposed to continue this way, and this becomes minus 15 cos 2t. And since minus 15 cos 2t is here, we can easily push it to the other side because there's a forcing term, by the way. This is going to be the forcing term, okay? Because I remember I explained this a lot in when we're talking about these in the other classes we had. So this is going to be the forcing term, all right, for the second order differential circuit that we have. This is going to be the forcing term. All right, let's take it a step further. So if we have it this way, I believe you know exactly how we got here now. If we have it this way, the next thing you want to do is to differentiate and divide by 2 to get the system equation. We need the system equation, so you just differentiate all of these here, okay? So when you differentiate everything that we have here, you would obtain d squared I, dt squared, all right, plus the I dt, because this is too high, okay, this is 2. If you are dividing everything by 2, those 2 will disappear. And then plus 5I. So what you find out here, okay, so if you have these, it becomes plus 5I equal to minus 15 cos 2t. Don't forget, we are differentiating everything. We are differentiating everything, okay, and dividing by 2. When you differentiate cos, you will obtain minus. That is how we got this minus here. And then this is 2t here. If you differentiate it, there will be 2. So this should become 15 minus 15 times 2 sine 2t. At the end of the day, that 2 is going to cancel out. So you are left with just minus 15 here. Also here you have 10 here. You just be left with 5 here when this is divided by 2. And then when you integrate I of t dt, you obtain I here. And this is what you do have. All right. So if we have it the way it is here, we can then go ahead and say this is our forcing term now here, as you can see, because we're looking for our forced mesh current. Assuming this was a constant, let's say this was just equal to 12 or equal to 15 or 30 or 100 or anything, our trial force solution will be assumed to be A. All right, but this time around we have to assume a trial solution that is going to be trigonometric function, because our forcing term is a trigonometric function, and for a trigonometric function, this is how you obtain what you use for the forcing term, what you assume to be the solution to the forcing term. All right, we talked about this too in some of the teachings we had recently. Okay, so I equal to A cos 2t plus B sine 2t, because we have 2t here, there has to be 2t here, and then going to be A cos plus B sine. All right, once you have these, the next thing you want to do, don't forget, we are trying to find this forced mesh current without using phasors at all. So you will notice that we have not even done any phasor conversion since we started. So since we know our I, and we have this system equation, if you differentiate this, you would obtain your di dt. So you can bring that your di dt and put it straight up in here. Okay, so if you differentiate it again to obtain the squared I dt squared, you would obtain a value. You bring that and then put it right in here. So if you put both in there and then you put your I here, you equate them to this. This is what you are going to obtain right up to this particular form. All right. Once you get this, what you will need to bring back to bear is your understanding of partial fraction. At this particular point, the easiest way to deal with this is to use partial fraction, to handle these. And how do you use partial fraction? Okay, you can see we have minus 4a here. All the coefficients of course, you bring them together. Okay, so first of all, before you do that, you probably just want to even simplify, remove this bracket and simplify. Let's get a simpler expression. So this is minus 4a cos 2t. This is another plus 5a cos 2t. All right, so that's why you can see we have minus 4a here. You have plus 2b, that's the coefficient of another coefficient of cos 2t. You have plus 2b here, and then you can see you have plus 5a here, basically. Okay, so, and all of those, they have cos 2t. They are the coefficients of cos 2t. Plus, what are the coefficients of sine 2t here? You can see we are starting with minus 4b. We have minus 4b here. Here again, we have minus 2a. You have minus 2a as coefficient of sine 2t. And then you can see here we have plus 5b here as coefficient of sine 2t. Okay, so, and then you can see we have our sine 2t here. We have our cos 2t here. So if you have all of those coefficients like that, it becomes easier for us to be able to know what to do next. What you do, according to partial fraction, I'm just going to quickly rush through this, is that you equate all the coefficients of cos 2t here, you equate it to the coefficient of cos 2t on the other side. Here, cos 2t, there's no cos 2t here. So the coefficient of cos 2t here is going to be equal to 0. All right, that's why there is no cos 2t here at all. Okay, so you are going to say minus 4a plus 2b plus 5a will be equal to 0. Under normal circumstances, minus 4a plus 5a is the same thing as a. So 5a minus 4a is a. So you have a plus 2b here. So that's why you have a plus 2b equal to 0. Okay, you look for the coefficient of sine. Minus 4b plus 5b here will give us just b. So 5b minus 4b is b. We have b minus 2a. As you can see here, we have b minus 2a. Then what is the coefficient of sine 2t here? It will be minus 15. So you equate that to minus 15. So you get b minus 2a equal to minus 15. If you solve these two equations simultaneously, okay, you obtain b equal to minus 3, a will be equal to 6. Okay, at the end of the day, if you have these two here, the problems become, the solution becomes very obvious. If you have, you have your a, you have your b. What you do is just you come here, and then you substitute your a and b into this particular expression, the first solution that we assumed. So, or your trial for solution. So a is 6, so you're going to have 6 cos 2t. B is minus 3, you're going to have minus 3 sine 2t. Once you have that, the next thing you do is you can easily find the magnitude and you can find the phase angle from here. You just convert it back to the magnitude and the phase angle. It becomes very easy. To get the magnitude, it will be 6 squared plus 3 squared. All right, 6 squared plus 3 squared is what's going to help us to get the magnitude. That should give us 3 root 5 if you do that. All right, so, and we have cos of 2t, by the way, we have cos 2t here. What will be the phase angle? Phase angle would be tan inverse. Phase angle would be tan inverse of b over a. Okay, so it will be tan inverse of minus 3 divided by 6. And if you find that tan inverse, what you're going to obtain is that the phase angle is going to be 26.57 at the end of the day. As a matter of fact, it will be minus 26.57. So that minus is going to cancel the minus you see here, and then this becomes plus. This minus you see here is as a result of this minus 3 in the first place. Okay, so you have 26.57 degrees here, and this becomes the current that we are looking for without using phasors. Again, what happens if we decide to use phasors? Phasor representations. Okay, you can see we have the circuit. So the question you want to ask yourself is, how do we deal with that? For phasor representation, we need to find the phase voltage and then find the impedance, and then the phase voltage divided by the impedance will give us a current that we are looking for. The voltage that we were given is 15 cos 2t, and like I told you, the phase angle here is 0 because this is just 2t. It's the same thing as 2t plus 0. So you can see that the amplitude of the voltage here is 15. So the voltage source in phasor form will just be 15 with phase angle of 0. That's exactly how we got the phase voltage here. That's exactly what we do have here. Okay. The next thing will be to convert this 2 Henry to Phasor representation. XL, which is our reactive component of the inductance, XL is usually equal to JWL. Let me quickly show you that. XL will be equal to JWL. So the impedance for that is going to be JWL. Okay, you can see here for the inductor. Okay, and for the capacitor, it is usually 1 over JCW, which is simply as minus J over CW. Okay, so I just needed you to remember that. All right, so in this particular situation, so to convert 2 Henry to inductive or reactive component of phasor representation, it will become XL, which will be equal to JWL. All right, so you have your J. What is going to be our W? Like I told you, this is supposed to be WT. So W is 2. It becomes J multiplied by 2 multiplied by L. What is L? L is 2. So 2 times 2 is 4. So you have J4 here. That's exactly how we got this J4 here. All right. The same thing goes for the resistance here. It's just going to be 2 ohms because this is already a resistive component. So you leave it there. And then to convert this to its impedance, okay, to convert these capacitance to impedance, it becomes, so that would be the same thing as saying we have XC. We are looking for XC. So our XC would naturally be equal to minus J over WC. That's what we have as SC. Okay, our W is 2. Our C is 1 over 10. So you have times 1 over 10 here. So this becomes 1 over 5. So eventually our XC will just be equal to 1 over 5 will just be equal to 5. So this becomes minus J5 at the end of the day. That's how we got here. All right. So we have all of these. If you add everything together, it gives you the equivalent impedance in this particular circuit. So let's see what comes out of it. Let's add everything together and see what happens. If you add everything together, this is what you have. J4 plus 2 plus minus J5. That's what we have here. So this becomes 2 minus J. This is what you obtain. Again, our V, we already know our V to be 15. Phase angle 0. That's what we have here as a numerator. So if you go ahead and fix this, what do you have? You can also write this 2 minus J in phasor form. How do you write 2 minus J in phasor form? This is pretty much easy. All right. This becomes, first of all, you find the magnitude. 2 squared is 4 plus 1 squared, which is, or plus minus 1 squared, which is 1. 4 plus 1 is 5. Square root of 5 is going to give us this. So that's how to find the magnitude of this particular complex representation. So if we go ahead, what you would have is this becomes this. The phase angle, like we said, will be tan inverse of B over A. B here is going to be minus 1. A here is 2. So that's tan inverse of minus 1 over 2. That's tan inverse of minus 0.5. If you check that out, you will get it as a minus 26.57 as a phase angle. So you can know this. So you can see this. What we have at the top here is still our phasor representation of the voltage. Now we have our phasor representation of the impedance, as you can see. So this becomes easier to deal with right now. 15 divided by root 5 using conjugates, you obtain it to be, this becomes 15 times 5 times root 5 over 5 automatically. Okay, if you remember your swords. If you're forgotten, you can go dust, your understanding up. 5 here 1, 5 here will give us 3. So you have 3 root 5 at the end of the day here. That's how we got this 3 root 5 here. All right. Again, for phase angles, we are going to subtract the phase angle of the denominator from the phase angle of the numerator, and that gives you 0 minus what we have at the denominator. So since we already have another minus here, it becomes 0 minus 26.57. That becomes plus at the end of the day, and that's why we have just 26.57 right up here. So if you have these, you probably want to now write these in as in a waveform representation. You want to write this in a waveform representation, and that becomes 3 root 5 cos 2t plus the phase angle. The phase angle we obtain is 26.57, and that becomes 26.57 here. The amplitude we obtain for the current is 3 root 5, by the way, so you have that here. And this gives you your current. What you would observe here before we go is that the two I's are the same, with or without using phasors. The answers to the current to the circuit, the first mesh current, are the same, with or without using the phase representations. Okay,